In this video, we're going to talk about electron configurations and how that relates to magnetism. So there are three main kind of divisions in magnetism. The first one is paramagnetism. So that one is when material with unpaired electrons So, due to their dipole moment caused by these unpaired electrons, they align to cancel out. So, we'll show a picture in a second that kind of describes that a little better. And then, when a magnetic field is applied, atoms can arrange to line up their spins in the same direction. And that is going to increase or reinforce that magnetic field. So now let's draw two little quick pictures here to kind of explain what we're talking about. So first, if we think about it, this would be like an electron that has a 3D orbital. So we're just going to show the 3D one here. So we have 5 orbitals here, and they have electrons in some of them. They have some unpaired electrons, but it's not half of them are full up, and they're not all full up. So this would be like an example of paramagnetism. So then you can see that those charges are all going to be up or down, depending on how they fill in. So whenever atoms arrange, and I'm just going to put little ups and downs inside these atoms to signify which way they're arranged, they're going to arrange in such a fashion that those dipoles created by the different spins will cancel each other out. So you can see we have like an up spin next to a down spin, which is next to an up spin, etc. So therefore no net dipole is really seen. So now looking at when a magnetic field is applied, so with a magnetic field, they're all going to align with that field. So the field, let's say, has a dipole in this direction. When we add in all of our atoms here, whatever material we have, they're all also going to go in that same direction. Because the force of that magnetic field is going to be stronger than those dipole forces. Now let's look at diamagnetic materials. So when we look at diamagnetics, those materials have all paired electrons. And when we say paired, we mean that in terms of the electrical configuration orbitals. So not necessarily as much bonding, but just we're talking about how we draw these orbitals out. So they're going to have a tendency to oppose magnetic fields. And since they're all paired, so they cannot change their alignment in order to match the magnetic field. So internally within the atom, they've already canceled out their magnetic potential, or that dipole. So you can't really change that. So a little example we could have here, have all of these, and they have an up and a down inside the atom. So they're already magnetically neutral just as one atom alone. And no matter how you would try and rotate those ups and downs, they're all going to have to balance each other. So an electrical or magnetic field isn't going to change that. And an example of a 3D orbital that would be like this is when all of them are full. So you have an up and a down in each one. And we're looking mostly at these d orbitals. Those are the ones that make the most difference in magnetism. Okay, so lastly we're going to talk about ferromagnetism. And those have unpaired electrons, like the paramagnetics. And their electrons are going to spin they're going to tend to parallel each other. And that's without a magnetic field. And that's because the atom can reside in a lower energy state, which is more stable. When aligned this way. So these are examples of our everyday magnets, like a fridge magnet. So looking at them, their 3D level generally looks like this. It's usually half full. And that's because of the wave duplicity that these electrons have. They can line up in a special way that is quite complicated, but all we need to remember is that it's half full, and that produces this ferromagnetism. So, drawing our picture like we have been in the past, these guys just in their normal state, not even with the magnetic field applied, are all going to go in the same direction. And some might be slightly skewed off, and that's normal, but depending on the strength of the magnet and that atom is at being a ferromagnet, they will be more and more aligned. So real quick, we're going to go over some just examples of ferromagnets. And iron is a big one. There's Fe3O4, which is called magnetite. Very creatively. And then one of the very strong magnets that is used in many commercial applications is going to be the neodymium. I'll spell it out here and let you decide how to pronounce it. And lots of strong magnets are going to be this type of magnet. And that is how the electron configuration and the magnetism are very closely related.